So here's a quick review. So we're talking about an introduction to estimation and detection. And I said, Kitty, there are two classes of estimation problems that we're going to be dealing with. The first is estimation of things that are random. So we're estimating random or detecting random variables. And the second class is going to be estimating parameters, which are unknown, but yet they are deterministic. So for example, estimating the mean of a Gaussian distribution or any distribution. Okay. So that's going to be class 2, and that's going to come a little bit later. We're right now discussing class 1, which is estimation or detection of, of things that are random, right? And then I made a distinction between this detection and estimation. The estimation may be rather broad, which covers actually both of them. But when we talk about detection, so detection is specifically applicable to, or specifically refers to estimation or detection of discrete random variables. So when you're trying to infer some information about something which is discrete, I mean, whether you're discussing, for example, whether the bulb was short life or whether it was long life, or whether you're going to pass or whether you're going to fail, or whether you're going to get an A grade or whether you're going to get a B grade or whether you're going to get a C grade. So all of these variables are discrete. So when you're trying to make a prediction or you're trying to estimate what these random variables are, we typically say that these are detection problems. On the other hand, when you're trying to estimate something which is continuous, so we don't use detection anymore. We would rather say it's an estimation problem. An example could be you're estimating the temperature from a noisy measurement, as we're going to see in an example. Okay. Then we talked about two methods or classes of how you can estimate things. The first one was maximum a posteriori estimation, so which is map estimation, okay, in which which is actually equation number 1 and 2, right? So on your screen, can you see the screen? Yes, you can see the screen. So is equation 1 and 2. So equation 1 is applicable to detection. So when you're trying to detect something which is discrete, you just maximize the posterior probability. You want to find out, given the observations, you want to find out which one of the y is going to be most likely, which is the most likely to have happened. Okay. So you essentially optimize or find the y for which the conditional PMF of y is maximized condition on the observations that you observed or you're given. Okay. Map estimation, on the other hand, you're just maximizing the PDF of y. You're finding the point where the PDF of y is maximized given the observation. So that's map estimation. And then we said, Kitty, the alternate is maximum likelihood estimation or detection, in which you are, which is actually equation number 3 that you see. So you're just optimizing or maximizing, or you're finding the y which maximizes the probability or the density function or probability which makes some observations most likely. You're finding that y which makes the observations most likely. Okay, and they're linked together, and we said there's a linkage between the two. What was that linkage? Josefa? I mean, we said, Kitty, maximum likelihood and map estimation, they're linked together somehow. How are they linked? So, Josefa, can you try to answer?
So we said that the map equation will give the same answer as the maximum likelihood equation if the prior is constant.
Right. So prior is constant, which means the prior is uniform, right? So it's a uniform distribution. Yes. And the reason is because the posterior, maximizing posterior, is the same as maximizing the product of the likelihood function and the prior function. Okay. So which is something I've depicted here. So in equation 2, this thing here is the likelihood, okay, and this is the prior. So maximizing posterior is maximizing the product of these two. Now, if the prior is constant and it's not a function of y, right, that means maximizing this product is essentially maximizing this first term, which is essentially the likelihood function, okay, which is the objective function of the ML estimation. Okay, so therefore, when things are likely, with equally likely, map estimation and ML estimation or detection yields the same result. Okay, And typically we would employ ML when we don't know the priors, right? So that's when we typically employ ML. Okay. Now I'm going to start out this session with some examples. Now the first thing I want to ask is, is the text size okay? I mean, is that legible on your screens, or should I increase the text size here?
सर थोड़ा सा बड़ा कर दें
थोड़ा सा बड़ा कर दें. All right.
जी
So I can go back. मेरा connection वैसे ही lose हो गया. So all right, so I'm going to start out with, as I said, with an example, which is that of map detection. And this goes back to the bulb detection problems that we've done in the previous chapters, except that we're going to sort of generalize it to observations on multiple variables. And this example is actually from your textbook. So this is problem 5.72 in your textbook. Okay, so that's what I'm going to start out with. Now the problem is something that you're familiar with. So you have a factory floor, and which manufactures two types of bulbs: the long life bulbs and the short life bulbs. And X is a random variable which indicates, which correspond to their lifetimes, right? And the conditional PDFs are exponential. So we have the conditional PDF of X given S is 1 upon 100 e raised to power minus x upon 100 u of x. So therefore, so this is an exponential PDF with the mean of, the units are hours, so this is a mean of 100 hours, right? So if it's a short life bulb, the lifetime is going to be an exponential PDF with an average lifetime of 100 hours. Okay? And the long life bulb, similar to what we had earlier, is exponential. The lifetime is exponential with an average lifetime of 1000 hours. Okay? We also know what the priors are. So we know that the probability of S is 0.75, and the probability of L is the long life bulb is 0.25. Okay? Now, here's the thing. The thing here, or the thing that is different from what we did, which is now instead of testing just one bulb, you're allowed to test two bulbs simultaneously or one after the other, whatever. Okay? So you have now observations on X1 and you have an observation on X2, where X1 is a lifetime of the first bulb and X2 is a lifetime of the second bulb, right? Or the life that you observe of the second bulb. Okay? And you want to make a decision on whether the bulb is a long life bulb or a short life bulb, depending on whatever observations you've made, right? So given that x1 equals small x1 and x2 equals small x2, we need to decide whether that box that we came across is S or L. Right? So the same problem that we've done before, except that we are now testing with two bulbs, one after the other, right? Or simultaneously, whatever. Okay? So how do I formulate this problem? So I'm going to try to formulate this as a map problem, right? Which is a map detection problem. So what do I do? I mean, what is that formulation? Can somebody help me here? Ji Nazish?
The probability of bulb being short life given x1 and x2.
Okay. Right.
Right.
So I see, Kaji, I would determine the probability that the bulb is a short life bulb, and that random variable is a random variable which takes on either a value of S or either a value of L. Okay, so that Y is really S or L. So we say Kaji, Y equals S. So let me rephrase this here. So y equals s and y equals l, right? Just to be consistent with some of the notation that I defined earlier, which is y is a parameter or y is a variable that we're trying to detect or estimate. So I want to find out what is the probability that the random variable y equals s given that x1 equals small x1 and capital X2 equals small x2, right? And I just want to see, is this, when will my decision be short? When this turns out to be greater than probability y equals L given x1 equals x2. So okay, let me try to formulate this as a, in the same setting that I just described up above. Okay. Right. So I have small y here given x1 is equals, and my y hat is going to be equal to argument max, and I'm going to search over those y's, all of the values that the random variable y can take, and it can take on two values, right? So either y is an element, is either that is equal to s or it is equal to L, right? And which one of these two maximizes this a posterior probability, that will be my decision. Okay, so that's exactly what we did earlier, right? Except that I've now formulated it or into the same kind of notation that I just described above, right? And since this is a maximization over only two variables, there are only two possible choices. That makes our life very, very easy. All we want to do is, I want to pick up, I want to value the probability for y equals s. I want to value the probability y equals L and just pick which one is a maximum, right? But since they must sum up to one, I can just see if s, the probability y equals s turns out to be greater than 0.5, my decision is going to be an s decision. Okay? And so I can conclude that probability y equals s given x1 equals small x1 and capital X2 equals small x2. If this turns out to be greater than 0.5, my decision is going to be s, right? And otherwise, if it's less than 0.5, my decision is going to be L, right? Giuseppe.
Sir, I just wanted to clarify something. Are we assuming that uh, basically x1 and x2 are two bulbs that we've chosen, and now we're trying to see that? So
Yeah.
are we assuming that both of them would be either belonging to the small one or the large one?
Yeah. So the problem, once again, let me reiterate that for you, is that you find one box on the factory floor, and you know for a fact all that box either contains all of them to be S bulbs or all of them to be long bulbs.
Oh,
Okay?
okay. So if we did not know this, that either
Then it's going to
that
be a
it's
problem.
all small.
But then there's no decision to be made.
Oh, okay. So if we pick up only one bulb and then we do the same thing, that probability that y equals y given x1 is x. So
Exactly. But now we're picking two bulbs, right? So you say,
okay.
and actually you can show that the probability of error is actually going to reduce if you pick two bulbs.
Okay, sir.
Okay, so what I'm doing is, एक मेरे पास box मौजूद है, and I know that that box is either a short life bulb box or a long life bulb box. Okay, and then I'm given the option of picking up any two bulbs at random, and I know, okay, if I pick any two bulbs at random, either both of them will be short life bulbs or both of them will be long life bulbs.
Okay, sir.
ठीक है, and what I do is कि मैं पहला वाला चलाया and I note के लिए how long does it take to fail, and that's small x1, and then I run the other one and see कि how long does it take to fail, and that's x2, and that's an observation I've made. ठीक है, apologies if I did not make this clear earlier. Is that clear now, Zaifa?
Yes, sir.
Okay, and now all we want to do is, so my objective here is to do what? My objective is, Kitty, try to determine a condition on x1 and x2 such that when that condition is satisfied, my decision will be a short life bulb. So that's what I'm trying to go at, right? So trying to get at. And then I use Bayes rule. In order to go further, I just use Bayes rule here, right? So probability y equals x given x1 equals x1 and capital X2 equals small x2 is just equal to the joint probability of x1 and x2 evaluated at x1 and x2 given y equals s divided by probability y equals s. Oh, sorry, multiplied by probability y equals s. And then there's a divided by here. Divided by what? The joint PDF of x1 and x2. And let me use Bayes rule here. So this is given y equals s times probability y equals s plus f of x1, x2, x1, x2 given y equals L times probability y equals L, right? So far so good, right? Let me pull this up. And then I just want to see, is this greater than 0.5 or less than 0.5? Okay. Now, there's an assumption I can make, and that assumption is, okay, given y equals s or given y equals L, I can assume that x1 and x2 are independent. Okay? Does that make sense?
Could you repeat what you just said?
So my assumption here is, okay, given that y equals s, right, I would assume that the lifetime of the first bulb is independent of the lifetime of the second because they're independent bulbs. Take there are two different bulbs. The probability or the PDF of the first one failing, whatever that distribution is independent of the lifetime of the other. ठीक है, दोनों एक दूसरे से independent है, given that we know that they're both like short life bulbs. And so the similar thing applies for y equals L as well. Okay? So that's a fair assumption to make, right? So assumption here is, okay, assumption is conditioned on y equals s or y equals L, x1 and x2 are independent. Okay, so that's an assumption I can make. If that's an assumption I can make, what can I say about the conditional PDF? So this implies that f of x1,
Product of the individual PDFs.
exactly, right? So f of x1, x2, small x1, x2 given s, this is equal to f of x1, this is equal to f of x1, x1 given s, right? Or given s means y equals s, okay? Times f of x2, small x2 given s, right? So this is assumption. This is because of that assumption, right? Which is a fair assumption, okay? And similarly, f of x1, x2, small x1, small x2 given L is equal to f of x1, small x1 given L times f of x2, small x2 given L, right? And then what I do is I just plug in the PDF that I have up above, and I'm going to miss a lot of steps. And because it's just simple algebra, if you will, and I'll give you just the final result. So final result is the following. So you just plug in that PDF, you simplify things, and you will find, okay, this reduces to the following. I hope I've done my calculations correctly. So this is x1 plus x2. If it turns out to be less than 633.75, then your decision should be S. Otherwise, your decision should be long. Right? So the final condition that it turns out that is on the sum of the lifetimes of the two bulbs. Okay, which is based on that map estimation or map detection principles. जी शोएब.
सर अगर हमारे पास यहाँ पे शॉर्ट लाइफ बल्ब एंड लॉन्ग लाइफ बल्ब है, if we had say 5 types of bulbs, short, mid life and so on, then would we be able to obtain this final result as such कि x1 plus x2 less than है तो the threshold?
Not necessarily. So the kind of result that you would obtain in that case would actually be if अगर exponentials ही होते तो they would be I think a linear region though. So an intersection of lines उस तरह की आपको मिलती. So you would have had to compare type 1 bulb with type 2 and type 3 and type 4 and type 5, right? So if the condition was satisfied, if the probability was greater than all of the other probabilities combined, okay, or simultaneously, that's the region where you would have said, Kitty, this is type 1 bulb and type 2 and so on and so forth. Okay, Shoaib, does that answer your question?
Yes, sir.
So you would have had to make, उस case में you would have to make many more comparisons.
Okay, sir.
Okay, जी ईशा.
सर एक पता नहीं क्यों कंफ्यूजन हो रही है थोड़ी सी. वो ये कि अगर हमने ये डिसाइड करना है कि वो शॉर्ट लाइफ है और लॉन्ग लाइफ है, और ये चीज़ डिपेंड कर रही है ऑन द सम ऑफ x1 एंड x2, तो फिर इट्स अ लिटिल हार्ड फॉर मी टू सी कि इनिशियली हमने कहा था कि वो इंडिपेंडेंट हैं, लेकिन एट द एंड आवर डिसीजन इज डिपेंडिंग अपॉन देयर सम. तो फिर how can we see that?
What do you think are the other? So the independence has nothing to do with the fact that this turns out to be a sum.
So doesn't it actually affect our decision into saying that if they turn out to be short life or long life, depending upon what the values of x1 and x2 are,
they can usme so the point here is that why x1 and x2 are conditionally independent, they are not independent. They are conditionally independent. So if you knew for a fact that this is short life, then they're independent. Otherwise they're not. Because the reason why they're not is because अगर पहला bulb बहुत जल्दी fail हो जाता है, right? Without you knowing it was a short life bulb, right? So then you could infer something about how long the other bulbs are going to take to fail. Because if the first one fails in a very, very short time, it's very likely the other one is going to fail in a short time as well, on average, most likely.
Yeah, that being conditional actually answers my question.
But the condition that's independent. Okay? Ji Ali, go ahead.
सर अगर more than 2 bulbs हमने pick करने हो, तो हम ये map और ML apply कर सकते हैं?
आपका क्या ख्याल है?
मुझे नहीं लगता.
नहीं लगता? क्यों?
अगर definition देखें तो
So definition में what is in the definition that stops you from applying map and ML?
सर फिर हम joint ले लेंगे probability.
नहीं, so I mean अगर ये 5 किस्म के bulbs होते हैं तो what is going to change in this optimization? So let's say this is equation number A. So the equation number A is going to change. How is the equation number A going to change? If there were 5 of these bulbs that you were testing. I mean, there were 5 types of bulbs.
x3 आ जाएगा, x3 is equal to small x3, फिर x4, x5.
That's not what I'm saying. आपका क्वेश्चन कुछ और था. आपका क्वेश्चन ये था कि टाइप्स ऑफ बल्ब्स अगर मुख्तलिफ हों. Is that what your question was, right? Right. So if your types of bulbs were not just 2, they were type 1, type 2, type 3, type 4, type 5. Was that your question?
नहीं, मैं पूछ रहा था कि यस सर, यही था.
यही था ना. तो फिर उसका ताल्लुक x1 और x2 से क्या ताल्लुक है उसका? So there's no link with x1 and x2. The reason why you test 2 bulbs is not because there are 2 types of bulbs. That's independent. Right? I could test 2 bulbs out of the same box, even if I knew that the types of bulbs were 5. I could test 2 bulbs, I could test 3 bulbs. That's my choice. That's my design choice. And that it makes intuitive sense as I keep on increasing the number of bulbs that I'm going to test, I'm going to get a more and more accurate detection. Okay? And so what I've not done here is I would ask you to compute the probability of error in this case when you're testing 2 bulbs, and the probability of error in the case when you're testing 1 bulb. And that's I'm leaving off as an exercise. Okay? Okay. So agar ye 5 bulbs hote, to the only thing that would have changed was here. Here. Yahan pe instead of searching over 2 possible values of y, you would have searched over 5 possible values of y. And that's the only change that you can have. Okay? Uzaifa, you had a question.
Yes, sir. Sir, I wanted to ask that instead of finding a conditional probability and proving that if it's less than greater than 0.5, can we do that proving that the conditional PDF value of conditional PDF of 1 is greater than the other? Like,
yeah, that actually yields that yields is for greater than 0.5 and less than 0.5 for the case of 2 types of bulbs.
Two bulbs. Okay.
If it's not 2 types of bulbs, so phir aapko you cannot do this greater than 0.5 or less than 0.5, or for that matter greater than 0.2 or less than 0.2. Okay, you have to be more careful in that situation, and that's where you actually compare the 5 of them together and pick the maximum one. अगर सिर्फ 2 चीजें हैं वहां पे maximum pick करना बड़ा आसान है, क्योंकि all you can see कि अगर one of them is greater than 0.5, the other one is guaranteed to be smaller. And that's why just comparing with 0.5 suffices. It's an if and only if.
Okay, sir. And as we discussed last time, we can ignore the denominator when we're finding probabilities for more than 2. Okay.
Yeah, when comparing.
Yes.
When comparing. Ji. Ji Shoaib.
Sir, we should be able to come up with values of x1 and x2 such that कि अगर मैं वो values of x1 and x2 रखूँगा, तो the probability of the bulb being small will be the greatest, isn't it?
That's what what the final result stays for you. And what the final result stays for you, if the sum of x1 and x2 is greater than 633.75, so then the probability of the long bulb is going to be higher than the probability of the short bulb. Right? And vice versa when x1 plus x2 is less than 633. So that's a condition that we've actually developed.
Okay, sir.
Okay. Any other questions? Okay. What I'm going to do next is example in which now I'm going to try to illustrate the principle of maximum likelihood estimation. So this is example 2. And this is now estimation, not detection per se, right? So I'm not trying to detect something which is discrete. So this is not either this choice or this choice or this choice. The number of choices for the example that I'm going to do next are infinitely many, right? So the choices lie on a continuum of values on the real axis, okay? And that is a practical problem of trying to estimate some parameter or some random parameter, random variable from noisy measurements, from multiple noisy measurements, right? So this is with temperature sensing, right? So the thing that I can cast this in is is temperature sensing, or for that matter, agni sensing. So, right. So consider n temperature sensors. Which are in a room whose measurement is corrupted by noise, right? So there are n sensors that I place inside the room. Okay, all of them are temperature sensors, but each and every one of the measurements from these temperature sensors are noisy, right? Noisy in the sense they are a noisy. They are, the value or measurement is equal to the actual temperature plus some noise. Okay, so this is the model that I'm given, right? And which is very practical model, right? Many systems can be modeled like this, right? Where I equals 1 to all the way up to n, so which is which is the number of sensors. Okay. Now, what are these variables here? Y is the temperature you're sensing, right? So this is a quantity that is unknown to you, right? This is something which you're trying to measure, right? And there's no way you can actually measure it perfectly, right? Because whatever you measure it with, the sensor will definitely add some noise because of, for example, electronic components on top of it, or because of thermal noise in the electronic components, right? And that thermal noise is this variable Ni, right? So this can be modeled as a thermal noise, and which can be modeled as being Gaussian, which is zero mean, that's a good model. And variance, there's some variance to it, which let's say something we know, right? The sigma e squared, right? So this is the model, and this xi is the measurement of the ith sensor. All right. This is the measurement of the ith sensor. Now, what will be our objective? Our objective is so this is the objective. So our objective is, given observations x, I'm going to use x1, x2, all the way up to xn, determine or estimate y. ठीक है, आपको noisy measurements हैं, 10 sensors लगे हुए हैं, उन्होंने हर एक ने noisy measurement दे दिया है, right? Now, before I go with the actual derivation for this, I mean, what would be your intuitive guess? I mean, so you're all engineers, right? So what comes to mind off the top of your head if you have 10 noisy measurements and you want to reduce the effect of the noise? क्या करते हैं हम? Ji Mohsin, you've done this a lot, right?
Sort of, sir. So take multiple readings or average them out, तो उससे एक reduction हो जाती है अगर noise additive होता है.
Exactly. So you take multiple readings and you try to average it out, right? And that's what engineers do typically. So when Mohsin, you say multiple readings, so there's the different connotations here, by the way. When those multiple readings could be, you measure the temperature.
Like the same quantity.
The same quantity, one in time. कि पहले मैंने measurement ली, and then I take another one, then I take another one, then I take another one, right? The only problem with that approach is what if the y was changing with time as well? Okay,
right.
But
simultaneous.
There's some assumptions you can make. The way I'm pitching this is that there are 10 sensors in a vicinity, in a room, for example, or in a certain geographical area, okay, which are measuring the same temperature, and I'm assuming the temperature remains uniform, okay? Or I have 10 measurements from different sensors, which measure the same thing. Okay, so that's a mathematically इसमें कोई फर्क नहीं पड़ता, लेकिन that's another way to put it, right? And I would say कि यार मैंने अगर असल temperature निकाला ना, all I would do is I would just average it out, right? That's what the an engineering thing to do is, right? It turns out, as we're going to see, that turns out to be the maximum likelihood approach as well for this particular model, right? And the benefit of whatever we're going to do next is going to be the fact that if I change this model, which can have practical reasons for it, this analysis is going to tell me, or analysis is going to help me in determining what the optimum thing to do is. And turns out in some cases, the optimum thing to do may not be just taking a simple average. It may be a weighted average. Okay? How do I give those weights? This derivation I'm going to do, which is next, will give me those answers. Okay? Will point me in the right direction. Okay? So what is that derivation? So the objective here is okay, once again, given the observations on the noisy measurements, I want to estimate the parameter y, right? I want to estimate the temperature y. And I am going to do, because I don't have the prior available. So that's the first thing. I don't have a prior on the temperature, right? So let me just do it with the maximum likelihood principle, right? And the maximum likelihood principle, if I can just put in the definition here, y hat ml is just simply argument max. I want to pick that y, which maximizes what? Which maximizes y given all of the observations of x, right? So this is y given x equals small x, right? So where I'm now using vector notation, right? And vector notation is really, so let me write down so this is x1 equals small x1, capital X2 equals small x2, all the way up to capital Xn equals small xn. All right, so this is an optimization problem that I need to solve. In order to solve, for me to solve this optimization problem. So Shoaib, you say something about, will the prior become the weights? Not necessarily. So I'll try to answer this afterwards, okay? So what is the next step now? Actually, sorry. मैंने map बना दिया. This is not, the maximum likelihood is not this. This is, Mohsen, is that what you were going to say?
Yes, sir.
Yeah, so this is map estimation. And because I don't have the prior, I cannot do map yet, right? So this is going to be f of x given y. And this is evaluated as the observation and given small y, right? So where my, I'm saying that x is x1, x2, all the way up to xn. These are my observations of the measurements, right? Now, what comes next? So what is this conditional PDF? So let me try to find what this PDF is. What is this PDF? F of x given y, x given y. This is f of x1, x2, all the way up to xn, evaluated at x1, x2, all the way up to xn, given that y equals small y, right? What do you think this PDF is going to be? Mohsen?
So could we assume independence or फिर product of individual PDFs का कर दें?
Okay, good. सबसे पहली बात ये है. So I'm going to give you an assumption here, and that assumption is here. Assumption is कि N1, N2, all the way up to capital N are independent of each other, and all of them are identically distributed. So which basically says that this n jo hai na, if I were to say this is a vector, that's a Gaussian with zero mean and covariance matrix, which is just a diagonal matrix. Okay? There are no off diagonal सारी की सारी चीजें zero है. That means every random variable in the noise vector is independent of each other. Because that's an assumption, and that's a fair assumption, right? Why? Because if there are and Gaussian noise, by the way, white noise is independent. He लेते हैं thermal noise की, which is कि ये मुख्तलिफ sensors लगे हुए हैं, तो सब मुख्तलिफ sensors की जो noise है वो एक दूसरे से independent होगी. The realization of the noise is going to be independent. Okay, so that's an assumption I make. Given that assumption, what is this conditional PDF going to be? So you're given capital Y equals small y, right? So if you're given capital Y equals small y, so what will xi be? सबसे पहले ये बताएं. So given y equals small y, right? So if somebody tells you that I know that capital Y equals small y, right? So therefore there's nothing random about capital Y anymore, right? That's deterministic. That takes on some value small y. So in that case, xi is just some constant small y plus some Gaussian noise, right? So if I add a constant to a Gaussian noise, what is the distribution that I get?
Gaussian.
You get a Gaussian where what happens to the variance? What happens to the mean? Ji Mohsin?
So mean shifted Gaussian.
Mean shifted to what? Mean shifted to y, but the variance stays the same.
The constant.
Because you're adding just a bias to it, right? So all that happens is the PDF is going to shift, right? And this goes back to the linear transformation. I think I gave you something to work on your own, which is KG. If I add two Gaussian random variables up, it still says Gaussian. उसके means add हो जाते हैं और variances add हो जाती हैं if they're independent, right? And if you just add a constant to it, all this does is it changes the mean. It does not change the variance. Now, here's another point, which is if xi equals small y plus capital Ni, right? Given that this y is a constant, what can I say about the independence between x1 and x2? Are they still independent? Right? So x1 is small y plus n1. x2 is small y plus n2 and x capital N, small n is equal to y plus capital N small n. Okay? So if y is a constant, all of the randomness that comes into x1 is because of the randomness in n1. All of the randomness that comes in x2 is because of the randomness in n2, right? But since n1 is independent of n2, therefore x1 must be independent of x2 as well, given that y is a constant, right? That's an argument that I'm making. Is that argument clear? Right, so the argument is given y equals small y, x1, x2, all the way up to xn are independent of each other. Right, so that's an argument I made. And that's an important thing to understand, right? So is that clear? Is that argument clear? Kyun Maz?
Yes, sir.
Right, so किसी को ना clear हुआ? So once again, the argument is that if capital Y equals small y, so there's nothing random about capital Y anymore, so that's just a constant, then because all of the randomness is x1 is due to n1 and all of the randomness in x2 is in because of the randomness is n2. And since n1 and n2 are independent of each other, the randomness in x1 and x2 is also going to be independent of each other. So x1 and x2 are also independent. And the same argument applies to each and every one of the variables in the sequence, right? So therefore, all of them, x1, x2, x3, x4, all the way up to x sub n, all of them are independent given that capital Y equals small y. Okay? So using this argument, I can just write this conditional PDF or this joint conditional PDF as a product of the marginal PDFs because of independence, right? So this is just product I equals 1 to small n. This is f of capital Xi evaluated at small xi given y equals y, right? What does this turn out to be equal to? If I just multiply all of these things together, so this is 1 upon 2 pi variance sigma e squared t, and this is raised to power n by 2. There's an n because there are n terms being multiplied, by 2 is because there was a square root, okay? And everything in the exponentials, what happens there? They just add up. Disha?
Sir, I just said sum.
Yeah, sum. Good. And this is xi. Isha, xi minus what is the mean?
Y.
Y. Good. Whole squared. Right? So this is the likelihood function, right? So this is the likelihood function. Right? And what does the maximum likelihood estimation do given this likelihood function? Oops. क्या ऑप्टिमाइजेशन क्या होगी? Right? So this is the likelihood function. So this is the likelihood. And you need to optimize this likelihood function over what? Mohsen, sorry.
So the value of y that gives the most likely observation.
Right. So you remember, this is the maximum likelihood estimate is just going to optimize this objective function over this variable y. Right. This is the variable that we want to optimize over. Right. How do we optimize? We just take the derivative, and it turns out that this objective function turns out to be convex. Okay. So actually concave. Right. So this concave. So there's going to be a global optima or global maxima, and that global maxima is going to exist where at the point where the derivative as a slope is equal to 0, and there's only going to be one point. Okay. And so in order to maximize, what we do is, so maximizing, we make it, instead of differentiating everything here, I make an observation, which is maximizing f of x given y, small x given y over y is the same as minimizing what? Minimizing this term inside the exponential. Why is that?
Because the exponent has a negative sign.
Because the exponential has a negative sign and the exponential function is a monotone. Okay, because of the negative sign, the exponential function is monotonically decreasing in this term, xi minus y whole squared and summation outside. Okay, so therefore, if I minimize this with respect to y, that will be the same as maximizing the original thing. Okay, because जहाँ पे ये चीज minimize होती है, वहाँ पे दूसरी चीज maximize होती है, right? So that's the thing that I'm going to use. So therefore, y hat ML is actually the argument maximum over that y, which does what? That optimizes, sorry, ये minimum hai. So this is minimum. What is it does minimize? This minimizes this. I equals 1 to n xi minus y whole squared. Right? In order to minimize this, I am just going to differentiate this with respect to y, the objective function, right? So what is the derivative for this? क्यों अब्दुल्ला इसको डिफरेंशिएट करें y से क्या आएगा? Okay, Josefa?
So will we have minus?
Yeah, that's fine.
Minus xi minus y whole square.
So there would be no whole squared. I mean, so you just use the chain rule.
Oh yeah. Oh, okay.
Okay.
Sorry.
So this is just minus 2 times I equals 1 to n xi minus y. That's it. So you differentiate this with respect to y, so to आगे पे then you differentiate minus y, and that's because you have a minus 1. Okay. And this must be equal to 0. Right? And so this implies, if this must be equal to 0, this implies that summation I equals 1 to n xi minus summation I equals 1 to n y must be equal to 0. And since y is a constant, it's not a function of y, I, so y turns out is going to be equal to 1 upon, so y hat ml, y hat ml, it turns out to be equal to 1 upon n summation I equals 1 to n xi. Right, so this is exactly what your engineering intuition told you. Right, just the average, right? Just take the average values, and that will be the maximum likelihood estimate. This is the best estimate in the sense of the maximum likelihood objective function of the temperature y. Okay, now there are many variations that I can give you. For example, like say, yeah, what if I knew for a fact कि जो पहला सेंसर है उसकी noise variance इतनी है, दूसरे सेंसर की इतनी है, तीसरे की इतनी है. So they may not necessarily be the same. So let's say there was some information I had available, which was, okay, one of them is a very cheap sensor. That means it's probably going to be very noisy. The other one is slightly more expensive. It's going to be less noisy. The third one is slightly even more expensive and is going to be even more less noisy. Okay? And given this information, so given the sigma 1 squared, sigma 2 squared, sigma 3 squared, what will be your maximum likelihood estimate? And the same principles or the same set of steps would yield the result for you. So it would turn out कि वो weighted average आपके पास आएगी. So Shoaib, that weighting that I talked about in the beginning would have been because of the differences in the noise variance across the sensors. Okay? And not necessarily because of the prior as of this moment. ठीक है शोएब?
जी सर, लेकिन अगर हम इसे पहले वाले तरीके से करते हैं, the name just slipped out of my mind, और उसमें priors थे, तो could we have मतलब use priors as the weight? No, we couldn't have.
So prior के weight directly linearity के अंदर नहीं शामिल हो सकते, right? So it really depends on what the prior is, right? So now it becomes a function, the objective function or the optimization becomes a function of what the prior turns out to be. Okay, and so let me so example 3, which is not something I'm going to do here, that's actually a solved example in the textbook. I'm going to leave that off as an exercise. This is example, I believe, 6.10. in the textbook. And what that does is it tries to determine a map estimate for the same problem, right? So let me just say a few comments here. So if I were doing a map estimation for the same problem, for the same temperature sensing problem, this would have been equal to argument max y and something which I wrote earlier, right, in the previous problem by mistake. So y given x, right? So this is something I would have had to optimize over. And because of the things we did in the last class, it turns out that this is, so using Bayes' rule, basically, this would have been the same as optimizing the product of the likelihood function with what? With the prior, right? So this is that prior. This is the prior. And this is the likelihood. And you're not just optimizing the likelihood, but rather the product of the likelihood and the prior. Okay. Where does the prior come from in practical situations, right? So this prior could, for example, be knowing for a fact, let's say you're measuring the temperature in outside of SSE, right? You're measuring the temperature outside of SSE in the month of November, right? On November 26th, okay? And there may be some prior information from the years past, which tells you that the temperature at Lahore, outside of the SSE building, that follows some distribution, right? So that it does not let your sensor measurement go off a whole lot. Okay? So for example, that prior measurement could tell you the temperature in outside SSC on November 26th from the past data follows a Gaussian distribution, which has a mean of, say, 16 degrees centigrade, okay? And a certain variance. And the way the mean comes from prior data, right? And the variance comes from prior data, prior experimental data that you already have with you, right? So that prior is something that somebody else tells you outside of this measurement system, right? And now there are measurements here as well. And MAP would rely on maximizing the product of these two things, okay? So one, एक चीज कहीं उधर लेके जाना चाह रही है, likelihood कहीं और लेके जाना चाह रहा है, but at the end MAP maximizes the product, okay? So the textbook example is exactly the same example in which the prior is taken to be some Gaussian distribution with a certain mean and with a certain variance, and the same optimization problem is solved and the result is given. The result is there in the textbook, okay? Strongly encourage you to take a look, okay? और प्रायर्स टिपिकली हम इस्तेमाल तब करते हैं सो दैट बेनिफिशियल तब होते हैं जब जो है वी नो कि नॉइजी मेजरमेंट जो हैं बहुत ज़्यादा नॉइजी हो सकती हैं, राइट? सो टू गेट रिड ऑफ आउटलायर्स इफ यू विल, आई मीन टू सम एक्सटेंट, right? And there's a lot more I can say. I don't want to do that, and we don't have a lot of time to do that, okay? Any general questions before I move? All right, so this is a reading assignment. This, by the way, is also related to one of your homework problems, right? The same temperature sensing problem in which the prior is given to you, except that the prior is not Gaussian, it's rather truncated Gaussian. Okay? So I know कि Lahore में, for example, इस दौरान जो है minus so some 5 degrees से नीचे नहीं हो सकता कभी भी, और say 25 degrees से ज़्यादा नहीं हो सकता कभी कभार. So I know the minimum and the max, and within the minimum and maximum it follows a sort of a bell shaped. So that's the homework problem. Okay. All right. Any questions? All right. So let's do a quick review of where we started from and where we're headed, right? So we started out with estimation, right, and detection. And I gave you two sets of methods. One of them was a MAP method of estimating or detecting things, okay? And then there was a maximum likelihood method. And then we did 2 examples, one for map detection, and the second one was for maximum likelihood estimation. And for the map estimation, I'm leaving this off as a reading assignment. And there are there's several problems in the homework that exactly deal with that. Okay. I want to move ahead to a third type of an estimation method, right? And that is, so this is a third type of estimation method, which is called the minimum, and which is also extremely popular or very commonly used. This is minimum mean squared error estimation, and which is actually, let me write down the acronym for this. This is MMSE. So have you ever heard of this? I know, for example, Mohsin has done some work in MIMO. वहाँ पे बहुत ज़्यादा इस्तेमाल होते हैं. Anybody else who has heard of MMSE? MMSE estimator. Yes, it is very, very related to least squares. And actually, I can argue that this is actually there's a sub problem, if you will, or a subset of the least squares problem, a generic least squares problem. Okay, apply to random variables, apply to stochastic variables. Okay, so Shoaib say yes. Anybody else? MSE का नाम नहीं सुना कभी? MSE. Maz, have you heard of MSE? Mean squared error.
No, I have.
So now where? Okay, so let's do this. At the very least, we're gonna do the derivation of this before we. Are we gonna be able to do an example? Let's see. Okay. So there's a variable y that you want to estimate, and let that estimate be y hat, right? So if I form an error random variable, okay, error variable, which is z equals y minus y hat, right? So y, of course, is the thing that you're trying to estimate, right? So you're trying to estimate this. And y hat is what? Y hat is your estimate. Right? And then I see in order to determine how good of an estimate I get at the end, I just take the difference, and that's an error, right? Z is the error between what I'm trying to estimate and the estimate that I've made. Okay? So will Z be random or will Z be deterministic? Azi, what do you think? Would Z be random or deterministic?
Random.
Random. Why? Because Y is random.
Yep.
And actually, Y hat is also random. Why is Y hat random?
Y hat shouldn't be random if it's our estimate, right?
Right, but the estimate depends on what?
Something.
What is that something?
Some determinant.
So Y hat is an estimate that you make from the observations of X, right?
And given X, आप हमेशा एक ही estimate बनाएंगे ना, आप ये तो नहीं करेंगे ना कि मैं इन observations के लिए अपना estimate change कर लेता हूँ. Same observation, same estimate.
That I agree with you. That I agree with you. For a given set of observations, Y hat is deterministic. But what if there was not conditioning there, right? So अगर मैं एक दफा sensor की measurement लेता हूँ and I get an estimate and I take another set of readings, do you expect the readings to be the same?
I guess in that scenario,
right? So my estimate is going to change with every reading as well. So that's why it's random, because the noise, if you go back to the temperature sensing example, my So this, yeah, right? So this y hat ml here is the sum of my observations or the average value of my observations. But my observations are random as well, right? There's no guarantee that the observation that I get today is going to be the same as the observation that I get in the very next second or the very next millisecond. Okay? So therefore, the estimate is also random. So y is random, and the estimate that you make is typically random as well. And therefore, the difference, of course, must be random as well. So z is a random variable. Okay, so z is a random variable. Now, one of the ways to get a good estimate is try to somehow minimize this error, right? I mean, that's one way to go about this. And actually, you should have asked, yeah, shouldn't this what we should start out with? Okay, I form an error, and then just try to minimize the error, right? So this is called error, and you want to minimize the error, but the error is random. So what do I minimize therefore? I mean, would it make sense to minimize the average value of z? Right. So the question is, should we minimize or should we attempt to find y hat which minimizes expected value of z? I mean, is that a good idea? Is that a bad idea? Is that an okay idea? Kyun, Isha? Is that a good idea? So z is random. I know it's random. I want to minimize something about z, right? So let me just minimize the average value.
No, that won't help.
Why not?
Because हम एक रैंडम वेरिएबल की एक्सपेक्टेशन को मिनिमाइज कर भी लेंगे.
Yeah.
So that won't actually minimize the error itself.
They can minimize the error, first of all, because the error is random. There's, I mean, I mean, just saying that I'm going to minimize the error, that doesn't make sense because the error is random. So you would have to minimize some parameter related to that randomness. And one of those parameters is the average value. Okay? When we say that the average value के मैंने minimize कर दिया है, is that a good idea? The answer is no. The answer, of course, is it's not a good idea because I could actually minimize the average error, and yet the the probability of the error being large would still be very, very high. Could still be very, very high. Okay? And the simplest counter example is that of a Gaussian random variable, right? Which has a mean 0, but the variance is very, very large. Okay? And then it's very, very likely that when you draw from that distribution, the error turns out to be on average very, very, so on average, your variation, the absolute value turns out to be very high, or the squared value turns out to be very high. Okay? The power in that random variable is very high. Okay? So that's minimizing the expected value is not a good idea. Instead, what you should minimize is either the expectation of the absolute value of the error, or, which we typically do, the expectation of the squared error. Okay? And so this squared should have given you this away as well, right? So a better option is to minimize expected value of z squared, right? So therefore, you're minimizing the squared, the average or the mean squared error. So that's what you're minimizing. That's why it's called the MMSE estimator. Okay? You're minimizing the mean value of the squared error. Okay, and that makes intuitive sense. So that is a good idea. as far as I'm concerned. I mean, that makes sense to me. Okay, Mohsen, does it make sense?
Yes sir, हम ADS में भी L2 norm को minimize करते हैं error के.
Right, but it's just like that L2 norm that you talk about in ADSP is not stochastic, I think.
So that I cannot say.
जी शोएब,
सर स्क्वायर का तो समझ आता है, एक्सपेक्टेड वैल्यू का मतलब समझ नहीं आता कि व्हाई आर वी पुटिंग दैट ऑपरेटर देयर.
आप चलिए मुझे इसको इस तरह बताएं कि स्क्वायर्ड वैल्यू को मिनिमाइज करने का मतलब क्या है? Z इज रैंडम, राइट?
एनर्जी मिनिमाइज हो रही है अगर स्क्वायर वैल्यू को हम
हाँ, नहीं, so Z is random, right? So Z squared is also going to be random.
Yes, and
right?
more random probably.
So what does it really mean that you're minimizing something which is random?
Make it less random.
उसका मतलब कुछ भी नहीं है. देखो, if there's a value that is random and you say कि जी minimize करो इसे, I mean that has no meaning whatsoever, because sometimes it could be here, sometimes it could be there, sometimes it could be, so that it takes on a spectrum of values with a certain probability distribution. What you can do is minimize some parameter associated with that distribution of that randomness, okay? And which in this case is the second norm, is the second moment.
Okay, and that parameter must be deterministic for one iteration से.
Exactly, because आप जब minimization की बात करते हैं, I mean optimization problems की बात करते हैं, तो आपका objective function जो है एक deterministic quantity होना चाहिए, right?
Yes.
I mean, because that's the only thing that makes sense. I mean, how do you minimize something which is random, which कभी इधर होता है, कभी उधर होता है? So there's no solution to that.
Yes, thank you sir.
ठीक है?
सर मुझे Z स्क्वायर का ही नहीं समझ आया, हम Z की पावर 10 को क्यों नहीं मिनिमाइज करते?
You can do that.
क्या अगर मैं हायर वैल्यूज ऑफ Z को करूंगा तो कोई फायदा होगा?
So that would, as far as the intuition is concerned, that would make sense as well. I could have had absolute of Z here as well, by the way, Ghazi. And that would have made intuitive sense as well, right? It's just that KT Z squared is the most commonly used because there's a solution to that.
ठीक
I think there's a solution to that. That's why it's so applicable.
Sir, could you explain again shortly that why we do expectation of Z squared instead of Z?
Why do we do expected value of Z squared instead of expected value of Z?
Yes, sir.
Right. So because I could give you many counter examples in which the expected value of Z may be very, very small, okay? Yet the error would be large, right? Because the error जो है अगर positive, if it's positive 10 or it's negative 10, as far as I'm concerned, positive 10 is as bad as minus 10.
Yes, sir.
Right? The sign doesn't really matter for me as far as the error is concerned. Right? But when you're taking the expectation, there's a chance that those very, very large positive values cancel when you're taking the average with the very, very large negative values. And which turns out that the average value 0 आ जाती है या बहुत कम.
Oh, okay.
Right?
Okay.
And so this is some distribution. This is, I show you. Your distribution आ गया. Right? The average value is 0. यहाँ पे 0 है. The average value is 0, but this is not a very good error that the distribution of the error is not very good.
Okay, sir.
क्योंकि उसकी power बहुत ज़्यादा है. Average power बहुत ज़्यादा है. So that's why it's the better thing to do is minimize the power. और ये ADSP में यही है कि जो least squares problem है. Right? Why do we deal with the squares? And that's the same sort of idea. I mean, how many of you are familiar with linear regression, which is the least square problem, by the way? कि आपने एक straight line, एक set of data points है, उसके ऊपर एक straight line fit करनी है. Right? When you're fitting the straight line, how do you fit it? I mean, what's the objective function that you use? क्यों हुज़ैफा?
So basically we make use of some weights and then we find the difference of basically we try to minimize the distance of the line from the weights, like
No, that's not what you do. अगर आप distance सिर्फ average distance minimize करना शुरू कर दें तो that's not a good solution. आप average distance squared minimize करते हैं.
Yes, sir.
Right?
Sorry.
Because positive error is as bad as the negative error. You want to make sure कि our signs don't cancel out when you do
Yes, sir.
fitting or
Understood.
regression fitting. Okay? And the similar idea applies here as well, except that now we have an expectation on average values. Okay?
Okay, sir.
Acha, we're almost out of time. Let me just, Mohsin, did you have a question? You raised your hand.
नहीं सर, वो गलती से दब गया था.
Okay. So, so a better option is to minimize expected value of z squared, and so the estimator that minimizes this is called the, or labeled as the MMSE estimator. Now, here's a theorem that I am going to do without a proof, but the theorem, the proof is there in the textbook. And that theorem just simply states that the MMSE estimator, right? So y hat MMSE is equal to expected value of y given x is a conditional expectation. This is the theorem, right? The estimator, given the observations x, if you've given the observation x, the estimator, which is going to minimize the mean squared error, is just the expected value of y given these observations. Okay? And given the observations, all you're going to do is going to find the mean value of y, and that mean value of y given those observations is that value which is going to minimize the mean squared error. Okay? So take this as a fact. The proof is there in the textbook. Okay? So proof skipped. But it's with a note here that's there in the textbook. Okay, I'm going to stop here. So and I'm going to talk about linear MMSE estimator in the next class. Are there any questions about this? No questions? All right, let me stop.